Hello and welcome to another video. In this video we're going to be working on k-inverse pairs array. And in this problem you're given an integer array nums, and an inverse pair is a pair of integers ij where I is less than j and nums I is greater than nums j. So given integers n and k, return the number of different arrays consist of numbers from 1 to n such that there is exactly k-inverse pairs. Since the answer can be huge, return it modulo 10 9 plus 7. And so here n is 3 and k is 0, so they tell you this is the only thing because you shouldn't have any inverse pairs. So basically anytime you have, like, the way to figure out these inverse pairs is if you have some numbers, let's say we have like 3 2 1, we can figure out for each of these numbers how many inverse pairs does that make. So whenever you have a bigger number that is before smaller numbers, all of those will make pairs. So like 3 2 will be an inverse pair, 3 1 will be an inverse pair, and 2 1 will be an inverse pair in this situation. So the only way to have 0 inverse pairs is you can't have a bigger number in front of a smaller number, and that's kind of like important for some intuition. So you have to have it like this. In the second example, you want one inverse pair. So essentially, for one inverse pair, you just want one bigger number in front of one smaller number. So if you use 3, then you have to have 3 like this, and then you can't have something like this because that would make multiple. So this would be 1, and also like this would be 1. So if you want to have 3 not at the end, you would basically have to have 1 3 2. Or alternatively, you can have 2 2 1 3 would be the other one, and they kind of tell you. So the real intuition you need, and this is a pretty hard problem. Honestly, I don't know how many people actually solved it without looking at some other stuff, and yeah, so I had to look at like a few other solutions to kind of figure out what's going on. And also because I did the contest problem recently, my brain just kind of fried. But essentially the main thing you need to figure out is there's like a few ways to figure this out. One is obviously you can just try to make like every single kind of array, but what you want to really do is divide this up into subproblems. So for example, if we have n equals 3 and k equals 1 in this case, right? What we want to focus on is just for a number that we place, how many inverse pairs will that make? And then can we get the subproblem? So like, let's say we just put a 1 here. If we put a 1 here, we have 2 and 3 left. So this 1 will give you no inverse pairs at all, right? Because 1 will be before the other numbers. And we have 2 and 3 left, like the order we don't have yet, but basically this will give you one inverse pair. So this will give you a subproblem of we want 2 numbers now with one inverse pair still, because this 1 doesn't contribute to anything. Similarly, if we put a 2 here, this 2, no matter what the order of the last part, will give you one inverse pair, because if we do like this will give you one inverse pair, and if you do this 2 will still give you one inverse pair. Now obviously the 3 might give you more, but I'm saying like the value you place now, that's what it will contribute. So that's kind of the subproblem, is you try to place one of the numbers, and then from there you do a subproblem figuring out how many inverse pairs will that number contribute, and the number of inverse pairs that number will contribute is, if you place it, how many numbers are there after that are smaller than it. And also you can recognize, I think this is also kind of hard, that the numbers don't actually matter because we're not actually going to be placing numbers. We more just need a count. So if we have like n equals 3 and k equals 1, like the numbers itself don't matter at all. So for example, if we're placing 1 2 3, the number of inverse, as long as they're unique, the number of inverse pairs will be the same. If we're placing like 1 10 20, the numbers will be the same, right? As long as they're unique, the number of inverse pairs will be exactly the same. So the numbers you have don't actually matter at all. But how many inverse pairs can we make placing one number given n and k, right? So the number of inverse pairs we can actually just given n. Like, how many inverse pairs can we make placing just one number? And so that number of inverse pairs maximum is going to be n minus 1. So we can make a range of inverse pairs from 0 to n minus 1. And let me just show you here. So let's say we want 0 inverse pairs. That one's pretty easy. We just place a 1. Like, let's say we have 3 numbers, we just place a 1, and then we have a subproblem. So this 1 won't give you any inverse pairs. If we want one inverse pair, we can place a 2, and then these 2 numbers, this 2 will contribute to an inverse pair, right? Let's say we have 1 2 3. Now, like, we have some other numbers here, 1 3 to work with. This 2 will contribute to one inverse pair because it'll be greater than 1. And if we want 2 inverse pairs, we can place a 3. And then we have a 1 and a 2 left. Regardless of the order, this 3 will give you 2 inverse pairs, 1 here and 1 here. So that's kind of like the subproblem. Given n equals something, you can reduce k by up to n minus 1. And so that's a subproblem. So for example, let's quickly show the tree now that we know like the numbers don't actually matter. We're not going to use the numbers at all. We're just going to use n and k. So let's say if n equals 3, k equals 1. One like recursive state can be n equals 2. And we didn't reduce k at all, so k equals 1. 1 is n equals 2 and k equals 0. And then 1 is n equals 2. Let's write it. Let's actually do this. N equals 2 and k equals -1. And so anytime we get a k equals -1, we can just break. So while we're calculating the recursive case for getting k, because we can subtract anywhere from 0 to n minus 1, we never want our recursive function is going to have some k that we're trying to get. And so if we went to too many, then that's always going to be invalid. So for example here, if n equals 3 and k equals 1, we never want to like subtract 2 from k to get -1 because then we made too many inverse pairs. But that's essentially the recursive function. So let's kind of sum it down, and you're going to see why this is problematic and kind of the trick to doing this. And I think it's pretty hard to come up with. But the nice thing is you will get to practice DP and bottom-up DP. So I'll suggest is just like do this kind of problem, get it to time limit exceeded, and then do the optimization to get it to pass. Okay. So we're going to do DP here. And like I said, and you can see it's going to get time limit exceeded because essentially you can see that like our function relies on n and k, and it's going to have a for loop subtracting anywhere from 0 to n minus 1 from k. So it's going to be like n times k times n, which will be, or it's actually be like n times k, which if both of these are 1,000 will be 10 to the 9th, and that'll be too slow. But it will get you almost all the way there, and then there's like one optimization that you can use to get it to work. So let's talk about like our DP function. So with state we're going to have, right, as always you need state, base case, recursive. So state is going to be n and k. Base case, there are a couple of this, and you can set this up in a bunch of different ways, but essentially base case is when k equals 0, no matter what your array is, no matter what n is, you want to return 1, right? Because let's say your array is like 5 numbers. Like I said, we established the number of the numbers doesn't matter, right? If it's like 1, 2, 3, 4, 5, or 2, 4, 6, 8, 10, or 1, 2, 7, 15, 35, it doesn't matter at all as long as your numbers are different. But for k equals 0, in order for this to happen, the array has to be strictly increasing to have no inverse pairs, right? So if we have 1, 2, 3, 4, 5, it has to be like this. So that's why it's a base case. But when k is 0, there's only one way to have this kind of situation. And because you're adding this up, you do need to have a base case that will return 1, and you need to have a base case that will return 0. Sometimes you don't need a base case that will return 0 if you just recurse appropriately, but so that's what we're going to have. So if k is 0, we're just going to return 1 because we've kind of like reached a valid state. And then I'll have one more base case, and you could do this a few ways. So your other base case, if this isn't true, you can say if n equals 1, let's close this. Okay, so if n equals 1, or, and I'll make sure I close the Slack as well so it's not annoying. So if n equals 1, if you think about what n equals 1 means, that means we only have one number, right? So if we have n equals 1 and k is whatever, we can't make any inverse pairs with one number. So if n equals 1 or n equals 0 and k is non-zero, then this is never going to work. So I'm going to say, so you can say if n equals 1 return 0. I'm going to say if n equals 0 return 0. Either one of these is basically the same thing, because you're not going to be able to recurse. Remember, you can only recurse n minus 1 times. So, or you can only recurse by subtracting n minus 1 from k. So if n equals 1, you will just recurse down to this anyway. So here we're going to return 0. And I'm going to write it this way for the bottom-up DP, because otherwise it's going to be one index, which is going to be kind of a pain to deal with. So it's going to be easier this way. So this is that. So the recursive is pretty easy as well. We just sum up every recursive case where we have n, or we have k minus, and then every value from n minus 1 to 0. And I'll kind of show this in the code. So essentially, like if we have n equals 5 and k equals 2, remember the most values we can sum up, the most values we can get rid of by putting one number at the front is n minus 1. So we could recurse down to like n equals 4 k equals, like if you subtract 0, it'll be 2. Then we can subtract 1, it'll be 1. Then we can subtract 2, it'll be 0. And we don't want to subtract any more than 2, so I'm just going to have a break case where anytime we subtract more than, like, we're only going to recurse down to k equals 0 or more. So these are going to be all the base cases, or not all the base cases, all the recursive cases, right, where n is going to be 4 for all of these, and these will be the different k values. So let's quickly take a look at the code here. And this is basically it. So you have a mod value because the number can get too big. You have an n and k. When k is 0, that means the array has to be in strictly increasing order. When n equals 0, or you could put in 1 here, and k is non-zero, you can't reduce k anymore, so you failed to return 0. And then otherwise, you just, from the range of 1 to n, remember we can subtract any number from 0 to n minus 1 from our k. So we do that, and if our new k is less than 0, we break because we never want any of those, and we just add all those up and return. So if we actually run this, you're going to see like it passes these test cases. But if we hit submit, then we're going to have an issue. So yeah, so try to submit, and we're going to get a TLE because, like I said, this is n cubed. So for this thing, it's too slow. So now what we're going to do is we're going to convert this to bottom up, and we're going to get rid of dimension, and we're going to practice this again. So if we take a look, what dimension do we want to get rid of, right? So where are we recursing? So we're recursing to n minus 1, and this new k value can be anywhere from k to 0. So it's going to be a big range. So the dimension you want to get rid of is n, right? Because every n value relies on the value before. So we can just store 2 arrays there, get rid of the n value, and now we'll have space k. It will still get a TLE, but then we need, like I said, we need one more optimization, and then we can get it. So let's kind of draw this out. So this one I am going to draw out because it's like the optimization is hard to see. Like I think normally for bottom up, I try to just not draw it out and try to figure it out quickly. But in this case, we'll try to draw. Let's see if there's actually a, yeah, let's use this instead. So let's get rid of this, and let's use this instead. And actually, I think we want a bigger square. We probably just won't fill out everything, so this will be fine. This is actually perfect. Okay, so here is our square. Remember, we're only going to keep our row at a time. So let's try to have an example that's like, or I guess we can even use this example, right? So let's say, and like I said, the dimension I always get rid of is the row. So because the dimension I'm going to get rid of is the row, I'm going to show the row as the thing I'm getting rid of. So this will be n, right? Because this is the dimension we're getting rid of. And then this will be k. So our initial array is going, like basically we're going to have row where n equals 0, right? So where n equals 0, we want to have all our k values. And the way, let's say we're actually solving for, actually, yeah, so let's see if we can get rid of something. Yeah, okay, so let's try to do this. I think this works. Yeah, there we go. Perfect. Okay, so let's say we are solving for n equals, yeah, so this will be good. So this will be n equals 4, and we're solving for k equals 3. This is our problem, right? So let's say this is our problem. We can actually do, I believe we can actually do n equals 4, k equals 4 as well, so we can actually keep this, and I think that'll be fine. Because k can get really big, so I think this will be fine. So let's say we're solving for that. So n equals 4, k equals 4. So we are going to start at this row 0 here, and this is k. And we're going to build up all the way to here, right, where n equals 4 and k equals 4. And then we just need to return this cell here, and that should be our answer, ideally. Okay, so let's fill out the first cell initially. So the first cell is going to be pretty easy. So this is going to be our base case, and these will all be 0, because you can't have no items and inverse pairs, right? Now for each cell, think about the range of k values we can get. So for example, for n equals 1, we can only subtract, like if we go back to our code, we can only subtract up to n minus 1 values, right? So like if we have n equals 4 and we place a 4 here, then these 3 values will be whatever, but we have 3 inverse pairs. So the most inverse pairs we can place by placing one of these is only n minus 1. So for n equals 1, we can't subtract at all from k. So all of these values will just be the one above, like this. So this is basically just going to be a copied cell. That's why I said initially you can return 0 if n equals 1 or 0, because it'll be the exact same thing. But I just wrote it like this to make it easier for like indexing. So now for n equals 2, we can subtract anywhere from 0 to 1 from our k. So here, we can subtract anywhere from 0 to 1. So if you subtract 0, 0 would be the one above, and then 1's out of bounds, so we're obviously not going to use negative k's, but it's going to be this range. So this will be 1. For this, it's going to be this range, 1, 0, and these are all going to be zeros. Then for this, we essentially can subtract anywhere from 0 to 2, right? Because if n equals 3, we can, by placing one number, we can make 2 inverse pairs, and that's true, right? If we put in a 3 and we have some other stuff, no matter what these are, if this is 1, 2, or 2, 1, no matter what, this 3 will contribute to 2 inverse pairs. So the range now here that we can subtract when we add up these things is going to be k to k minus 2. So that'll be this. So 1. So that's going to be 2 numbers, or it's going to be 3 numbers total, right? So that'll be this, which is going to be yeah. So this is going to be 2. That'll be this. So 1, then this, then this. Now finally for the last one, same thing. We can only subtract, if n equals 4, we can only subtract 3. So the range is going to be anywhere from the previous value of k to k minus 3. So this window will be 1. This window will be 3. So k minus 1, k minus 2, we still are covering the whole thing. So that'll be 4. Then here, k to k minus 3 is going to be these 4 numbers, right? So this is going to be 4. And finally here, we can only cover 4 numbers, so it's going to be 3. Hopefully I did the math right. If I did the math wrong, sorry about that, but essentially the concept is the same. Basically, for a given n, we can look at previous k to k minus n minus 1, right? That's the range we can have. So notice that, like, for example, for this, like, let's say this is n equals 4, k equals 3. We have to sum up the values at n equals 3, and k needs to be equal to 0 to 3, right? Because we can subtract anywhere from 0 to n minus 1. So for this number, the range is this. But for this number, the range is this. So let's take a look at these two ranges. So for this number, the range is this. And for this number, the range is this. So really what we did is we had like a sum, and we got rid of this number and we added this number. And that's kind of the idea. So you do this bottom-up DP, and then you optimize. Instead of having this third loop, you just keep track of a cumulative sum of a range that you can cover. So for example, for this, we can cover 4 numbers, right? K, k minus 1, k minus 2, k minus 3. It's going to start with most of them being out of bounds, but then we can keep adding numbers. So let's kind of walk through how that would go really quickly. So for this number, it's going to be this. Then for this number, we will add this. Then for this number, we will add this. For this number, we will add this. And finally, for this number, our window got too big. Remember, we can only cover 4 numbers. So we are going to get rid of this one and add this. And that's kind of the optimization we need to get it to go from n times k to now, because of this window, this will be in constant time. We're going to be getting these sums in constant time. So we got rid of this k, so now we'll actually have an n by k. And let's take a look at the code for that. And I do think this is kind of hard to come up with. I'm curious if anyone came up with this on their own. I think like a bottom up, like if these dimensions were not 1,000, if these dimensions were like 100, that's pretty reasonable. But like coming up with a bottom up solution and getting to the dimension is pretty hard. And I think you can also code this in memoization, but I think this makes more sense than bottom up with a sliding window. So we can comment this out, take a look at this code. So essentially we just start, remember we got rid of the nth dimension. So this dp function is going to be n equals 0. We set the base case. This is going to be the n dimension. I probably could have used better variable names for I and j. And then the same format as on all my other problems. You have a dp and a new dp. And a new dp is going to take every number from 0 to k plus 1, or 0 to k. And now the only thing we change is we just keep track of a cumulative sum. So we just say, okay, we keep track of a cumulative sum, and basically we just need to make sure that we need to make sure that we get rid of numbers if the window gets too big. So if the window gets too big, we need to subtract the number. Otherwise, let's just keep adding the number to our current sum, and then our new DP value will just be our current sum. So we're essentially just going through, adding a number, adding a number, adding a number, adding a number for whatever we're storing. And then once our window gets too big, let's say we can only hold like 3 numbers here, we're just going to get rid of a thing. And that's the basic idea here. So you use a sliding window to keep track of the current sum, which is going to use DP, because remember DP is the previous row. So when we're calculating this row, we're going to be storing the current sum of elements in this row. And we just need to, it's pretty easy to figure out like how many elements we can store, because if this is 4, then we can store 4 elements, right? We can store k, k minus 1, k minus 2, k minus 3. And anytime k gets to n or bigger, then we need to start subtracting. And so that's kind of what we're doing here, right? And that's kind of the same thing here. So if we go back to our windows really quick. So remember, for this number, the window was this. 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 And once we got to this number, k equals n. Once k equals n, you need to start subtracting. So that's kind of the idea here. Once k is equal to n, you need to start subtracting, and then you basically just return, and you just add it up. So we got rid of some stuff. So let's after submit first. And then, so this is pretty good. And now basically the time. And like I said, I think it's very hard to come up with. It's not super written out, so I kind of looked at some solutions to get an idea for like what we need to optimize. So here, now we have O of n times k, right? Because this is the n dimension, the k dimension, and for the space, we're only storing k. So we got this down a lot, right? We got rid of the n dimension with our space optimized bottom up. If you do a 2D matrix for bottom up, it will also pass, but that's essentially what we got rid of. So we're going to get rid of this code for the cache, because this is going to be a TLE, and this is the solution you want. And I think someone asked me to do like more bottom up, so hopefully, I think this is like definitely a hard enough problem to practice bottom up and space optimized bottom up. So yeah, that's going to be all for this one. If you have any questions, let me know. And if you did like this problem, then please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.